So calculus time, and we are up to chapter 4 on applications of the derivative. And the first applications have to do with understanding the shape of curves and understanding the shape of curves and what the graphs look like using information that we get from the derivative. So if you have a function whose graph looks like this, points like these, these are called local maxima. And points like these are called local minima. And a function f of, so this, suppose this is the graph of the function y equals f of x. A critical point of the function, so we say a is a critical point of this function if either the derivative at a is 0 or f prime of a does not exist. And of course, suppose we had a function which looks like this, and this is on some interval, say from a to b. In this interval, in this closed interval from a to b, this point is the absolute minimum. Because in this interval, actually, let's say do it like this. And this is b and this is a. We're looking at the graph of this function just on the closed interval from a to b. This is the absolute minimum. And this point looks like it's the absolute maximum. So if you're looking for the absolute maximum or minimum on a closed interval, you look at the local minimum and maxima, and you also look at the values of the function at the endpoints. And the absolute maximum and minimum will occur at one of them. So let's do a couple of problems just to try to make this a little bit more concrete. So here is a typical problem in calculus. Find the absolute extrema. That means the absolute max and the absolute min of a certain function on a certain interval. So for example, of f of x equals x squared minus 10 on the interval from 2 to 3. So interval from minus 2 to 3. So first we look for the critical points, CP, critical points. So where is the derivative 0? f prime of x is 2x, and that equals 0 at x equals 0. So this function is differentiable everywhere. The derivative is 0 only at x equals 0, and the value of the function at 0 is 0 squared minus 10, or minus 10. And what's the value of the function at the endpoints? F at minus 2 is minus 2 squared minus 10, which is 4 minus 10 is minus 6. And f of 3 squared minus 10, sorry, f of 3 is 3 squared minus 10 is 9 minus 10, or minus 1. So if we're looking at this function on the interval from minus 2 to 3, when x is 0, it has the value minus 10. When x is minus 2, it has the value minus 6. When x is 3, it has the value minus 1. So the graph of this function on this interval looks like that. And you look at these three values, the smallest is minus 10. So minus 10 is the absolute minimum. And the largest value is minus 1. So this is the absolute maximum. So for this parabola, I mean, the parabola itself, if you drew the whole thing, would look like this. It's just the standard parabola is shifted down 10 units. But we're only looking at it from minus 2 to plus 3. And in this interval, this is the absolute minimum. That's a critical point. This is the absolute maximum. It's not a critical point, but it's an endpoint of the interval. So that's a typical example. Any questions about that? No. Sorry about the background noise, but I'm working from my office at home and there are guys here doing some construction. Okay. Let's look at another example. Suppose we have f of x equals x cubed minus 3x squared, and we want to find the absolute extrema on the interval from minus 1 to 3. So this is a polynomial, it's differentiable everywhere. The derivative is 3x squared minus 3 times 2x, or 6x. So that's 3x times x minus 2. And this is equal to 0 at x equals 0 and 2. So these are the critical points for this cubic curve. And what is the value at the critical points? F of 0 is 0. F of 2 is 2 cubed minus 3 times 2 squared. That's 8 minus 12, that's minus 4. So these are the critical points. But we also have to evaluate the function at the endpoints. F at minus 1 is minus 1 cubed minus 3 times minus 1 squared. Minus 1 minus 3 is also minus 4. And f of 3 is 3 cubed minus 3 times 3 squared is 27 minus 27 is 0. So the minimum occurs at 2 points, 2 and minus 1 at 4. And the maximum occurs at 2 points at 0 and 3. Let's see if we can figure out what the graph of this function looks like. So this is the f of 0 is 0. F of 2 is -4. F of 3 is 0. And f of -1 is also -4. And the graph of this function is really going to go up, down, and up again. So the absolute maximum occurs at 2 points. And the absolute minimum occurs at another 2 points. The absolute minimum and absolute maximum do not have to occur at unique points. So that's a pretty function, and that's what the graph looks like. Any questions about this? Let's do some more problems. Let me look at, this is in the text. Excuse me 1 second. Zoom. Okay. So this is in the text on page 249, number 72. So we want to look at a box with a square base. This is going to be a box with a square base. And we look at all such boxes that have a volume of 50 cubic feet. So if the dimension of the base is x and the height is what? So let's see, that's interesting. So suppose that the side, the length of the base is equal to x. So in that case, the volume is the area of the base, x squared, times the height. And we're told the volume is going to be fixed at 50. So once you pick x, h has to be equal to 50 over x squared. So this is before we even start the problem. We have to solve a simple geometry problem. You have a box with a square base. Let's say the length of each side of the base is x. If the height is h, the volume is the height times the area of the base. The area of the base is x squared times h. But we're only looking at boxes whose volume is 50 cubic feet. So h is 50 over x squared. So now what is the surface area of the box? So it depends on x. So the base has area x squared. The top has area x squared, so we have 2x squared. The side is a rectangle, hx, area hx, and there are 4 of them. But h is 50 over x squared, so this is 2x squared plus 4x times 50 over x squared. So if I do my arithmetic correctly, this is 2x squared plus 200, 4 times 50, and x over x squared is x. So this is the surface area of a box of volume 50 and base x squared. And of all such boxes, we have the following extremal problem. Find the minimal surface area, the absolute minimum of the surface area on the interval x goes from 0 to infinity. So you look at all such boxes where the base has some positive length, and the surface area varies as a function of x. We want to know how small can the surface area be. And for such a minimum, find the dimensions of the box. Well, here we have a function. We want the absolute minimum. So we need to calculate the critical points. What's the derivative? S prime of x, the derivative of 2x squared is 4x, and the derivative of 200x over x is 200 over times minus 1 over x squared, minus 200 over x squared. And when is that equal to 0? For that to be equal to 0, 4x equals 200 over x squared, or x cubed equals 200 over 4 is 50. So x is the cube root of 50. And when x is the cube root of 50, s of the cube root of 50 is 2 times the cube root of 50 squared plus 200 over the cube root of 50. Let me try to simplify this a little bit. Cube root of 50 squared is 50 to the power 2/3. And this is 200 times 50 to the power minus 1/3. Let's see, can we simplify that a little bit? This is equal to, so 50 to the power minus 1/3 is the same as 50 over 50, is the same as 50 to the 2/3 over 50. And 200 divided by 50 is 4. So it looks like I get 6 times 50 to the power 2/3. Now, there's no endpoints to check. But we could take the second derivative. So for this function, if this is the first derivative, the second derivative is 4, and the derivative of x to the minus 2 is minus 2x to the minus 3. So we get plus 400 over x cubed. And that's going to be positive for x greater than 0. So we have the first derivative is 0 and the second derivative is positive, which means that we have a minimum. And this has to be the absolute minimum. So we have the absolute minimum when x is the cube root of 50. So we have x equals, sorry, not the cube root of 50, cube root of 50 squared, or 50 to the power 2/3, and the height h is 50 over x squared, which is 50 over 50 to the 4/3, which is 1 over 50 to the 1/3. So we have another way of writing this. X is the cube root of 50 squared, and h is 1 over the cube root of 50. So x squared h is the cube root of 50 to the 4th over the cube root of 50, which is the cube root of 50 cubed, which is 50, which is just what it's supposed to be. But the important thing is a little bit of calculus in here. We use the first derivative, and we also use the second derivative. If the first derivative is 0 and the second derivative is positive, by the second derivative test, we have an absolute minimum. Okay. Any questions about these? This book really has very interesting problems. Let's do a few more of these, because these are really a critical part of Calc 1. Again, oops. I'm on page 249. Let's look at number 73. So we start with, at the top of a cliff, 192 feet high, and we throw a stone straight up with an initial velocity of 64 feet per second. And if we look at the position, the height as a function of time, let's call this S, it goes up and then it comes down. That's sort of what we expect. And we're told, oops, let me draw this so you can see it, right? 192 feet above the ground, we throw the stone straight up, and if we look at its height, S, as a function of time, it's actually a parabola that's going down, and it's given by the function S is equal to minus 16t squared plus 64t plus 192. And again, the velocity, which is the derivative of the position, is minus 32t plus 64. And the velocity at time 0, you see, we get 64 feet per second. Right? This is the height in feet. The velocity is in terms of feet per second. When does the stone reach its maximum height? That is, at what time do we hit this maximum height? So we want to find the critical points, S prime of t. Well, here it is. Sorry, what's that? And when is this equal to 0? When is the derivative or the velocity equal to 0? That means minus 32t plus 64 is 0. 32t equals 64. T equals 2 seconds. So 2 seconds after we throw the thing up in the air, the stone reaches its maximum height. Let's look at a really interesting problem. Let's look at number 85. we have the function g of x equal to the absolute value of x minus 3 minus 2 times the absolute value of x plus 1. So if you're not used to the absolute value function, remember, let me graph over here. If we have the function y equal the absolute value of x, the graph looks like that. You take y equal the absolute value of x minus 3, that's the same graph, but it's shifted over 3 units to the right. So when x is 0, y is 0. And the graph looks like that. And if we want to look at the absolute value of y equal x plus 1, it's the same graph. This is 0 when x is minus 1. And it's this. So let me draw it in red so we can see which is which. So that's the absolute value of x plus 1. And then we're looking at this combination of them, x minus 3 minus 2 times x plus 1. So let's try and figure out what the graph of that is. Right? So what is the graph of y equals minus 2 times x plus 1? So this is the graph of y equal x plus 1. If you look at minus that, it's going down. And if you multiply it by 2, it's going down twice as fast. So y equal x plus 2 looks like this. At the point minus 1, you get 0. When x is 0, oops, didn't go so well. When x is 0, you have 0 minus 2. When x is minus 2, this is minus 1. Absolute value is 1, is minus 2. So this is minus 2, minus 2. Right? That's what this function looks like. And we want to find well, this is the problem. Find local and absolute max and min on the interval from minus 2 to 3. So let's see how we can graph this by hand. If you are using Maple, of course, you can get a beautiful graph with Maple, but maybe I'll do that in a moment. But let's see how we can do this by hand. So let me write down this problem again. This is number 85. G of x is the function, absolute value of x minus 3 minus 2 times the absolute value of x plus 1. And we're looking at this on the interval from minus 2 to 3. And the function y equals the absolute value of x minus 3, that function looks like this. What is this equal to? If x is bigger than 3, this is x minus 3 for x greater than or equal to 3. And for x less than 3, this is negative, so it's 3 minus x. And if we look at the function y equals minus 2 times the absolute value of x plus 1, what is that equal to? So see, we saw the graph of that function a moment ago. Graph of that function looks like that. So if x is greater than or equal to -1, this is what the function looks like. It has y-intercept -2 and slope -2. So -2x -2. And if x is less than or equal to -1, it has slope +2 and would hit the y-axis at +2. So this would be 2x +2. When x is -1, this is 0. When x is -2. So that's what this function looks like. And we're interested in this minus this. So let me just sort of draw a kind of a picture of what this function looks like where I have -1 and 3. So when x is greater than or equal to 3, y, which is x minus 3 minus 2 times x plus 1. When x is greater than or equal to 3, this is x minus 3. And when x is greater than or equal to 3, this is minus 2x minus 2. So this is x minus 3 minus 2x minus 3 minus 3 minus 2 is -5. So y is equal to minus x minus 5 for x greater than or equal to 3. Let me see if that's correct. Something doesn't look right, so let me just double check this. Yeah, that looks good. And when x is less than -1, y, when x is less than -1, x minus 3 is 3 minus x. And when x is less than -1, this is 2x plus 2. So this is x plus 5. And when x is between -1 and 3, when y is less than 3, this is 3 minus x. And when x is bigger than -1, it's minus 2x minus 2. So this is 1 minus 3x. When x is -1, you get 4. When x is 3, you get -8. So this is how we can describe the function. So if I want to graph it, let me try and do that. I want to graph it from -2 to 3. So at -2, the value of the function is 3. At 0, the value of the function is 1. At 3, the value of the function, oops. Maybe I should do this differently. Is -8. So at 0, the value of the function. So at 3, the value of the function is -8. And at -1, sorry, at -2, the value of the function is 3. At -1, the value of the function is 4. And at 0, the value of the function is 1. And at 1, the value of the function is -2. And at 2, the value of the function is -5. So what is the graph of this function going to look like? For -1, it's x plus 5. Here it's 1 minus 3x. Yeah, that's the graph of the function. This is -2, 3. This is -1, 4. This is 3, -8. So you can see that the absolute minimum is 3 minus 8. The absolute it's -8. The absolute maximum is 4. And the local maximum occurs right here also. Yeah. So it's an interesting exercise. Okay. We also last week talked about Rolle's theorem and the mean value theorem. So let me just review that and do a couple of problems. Rolle's theorem says you have a continuous function, and at some points A and B, the value of the function is the same, then there has to be some point, for example, C, between A and B, where the derivative is 0 for some C greater than A and less than B. So if you have a continuous function, and if f of A equals f of B, so on this closed interval from A to B, the value at the endpoints is the same, then the derivative must be 0 at some interior point if we have a differentiable and continuous function. And the mean value theorem is a kind of generalization of that. Again, we have a function which is continuous and differentiable on some interval from A to B. If you take the chord joining the graph at the endpoints of the function, so this is A comma f of A, and this is B comma f of B, the mean value theorem says there's some point on the curve, maybe right there, where the tangent line is parallel to the chord, or another way of saying that is f prime of C the derivative at this point is equal to the slope of the chord, f of b minus f of a over b minus a, for some number c in the open interval between a and b. That's the mean value thing. So let's look at a couple of exercises. So these are going to be exercises on page 255. Suppose we consider the function f of x equals x times x minus 1 squared on the interval from 0 to 1. So f of 0 is 0, f of 1 is 1. So by Rolle's theorem, f prime of c is going to be 0 for some c strictly between 0 and 1. And we want to find it. So for this function, f prime of x, this is equal to the derivative of x, which is 1 times x minus 1 squared, plus x times the derivative of x minus 1 squared, which is 2 times x minus 1. So this is x squared minus 2x plus 1, plus 2x squared minus 2x. That's 3x squared minus 4x plus 1. When is that equal to 0? Let's see. Maybe I'll be lucky and I can factor this. This might be 3x minus 1, x minus 1. Let's see, 3x squared minus 4x equals 0. So this equals 0 at x minus 1 equals 0, which means x equals 1, or 3x minus 1 equals 0, or x equals a third. But I'm looking for a 0 strictly between 0 and 1, so x equal third is the unique correct answer. Okay. What about an example for the mean value theorem? Let's look at number 21. Number 21, we have a parabola, f of x equals 7 minus x squared. So this is 7, this is the parabola opening down. And we're looking at this on the interval from minus 1 to 2. F of minus 1 is 7 minus 1, or 6. And f of 2 is 7 minus 4, or 3. So this is 6, and this is 3. So if I look at the chord, joining these 2 points, this is minus 1, 6, and this is 2, 3. So the slope of the chord, m, is 6 minus 3, or 3 minus 6 minus 3 over 2 minus minus 1 is minus 3 over 3 is minus 1. So this line has slope minus 1. f prime of x is minus 2x. That equals minus 1 when x equals a half. So x equal a half, that's this point. At that point, the derivative is minus a half, and the tangent line to the curve at this point is parallel to this chord. So that's an exercise in the use of the mean value theorem. What about concavity? So suppose you have a function f of x, which has a derivative, that means differentiable, on an open interval I. F is called concave up on I if f prime of x is increasing on I. And f is concave down on I if f prime is decreasing on I. And the function is increasing if its derivative is greater than or equal to 0. So the derivative of the derivative is the second derivative. So if the second derivative is positive, let's just make it strict. The second derivative is greater than 0 on I. And decreasing means the derivative is negative. So the derivative of the derivative is the second derivative. So where the first derivative is positive, a curve is concave up. Where the first derivative is negative, the curve is concave down. If you have a local maximum, the graph looks roughly like this. And in this region, the curve is concave down. Second derivative is negative at this point. If you have a local minimum, curve is concave up. And so the second derivative is positive at that point. And this is a way to, in many cases, but not all cases, but in many cases, determine whether you have a local minimum or a local maximum. You know that at a local minimum or a local maximum, you have a critical point, the derivative is 0. But that doesn't tell you whether you have a min or max or neither. But if the first derivative is 0 and the second derivative is negative, you have a local max. If the first derivative is 0 and the second derivative is positive, you have a local min. And that is what is called the second derivative test, which is infinitely important in calculus. So let's look again at some exercises. We'll go to page 267. And suppose we take the function and this is number 19, f of x equals 4 minus x squared. So the first derivative is minus 2x. F prime of x is greater than 0 if x is less than 0. So the function is increasing when x is less than 0. The derivative minus 2x is negative if x is positive, so it's decreasing there. And of course, if you graph this parabola, you see immediately that's correct, because the graph of 4 minus x squared is just this. And you see for x less than 0, the function is increasing. For x greater than 0, the function is decreasing. Let's look at number 23. We have the function f of x equals x cubed over 3 minus 5x squared over 2 plus 4x. And we want to find the intervals where the function is increasing and decreasing. So we compute the derivative. The derivative of x cubed is 3x squared, makes this x squared. The derivative of x squared is 2x, makes this minus 5x. Derivative of x is 1 plus 4. That's the first derivative. And we're lucky this factors into x minus 1, x minus 4. So what we can say is that f prime of x is greater than 0, either for x bigger than 4 or x less than 1. If x is bigger than 4, these are both positive. If x is less than 1, these are both negative. And f prime of x is negative when x is between 1 and 4. So we have 1, 2, 3, 4. The function is increasing for x less than 1. Between 1 and 4, it's decreasing, and then it's increasing again. We have the classic shape of a cubic curve. Let's look at problem 29. We have the function f of x equals x squared times the log, ln, log of x squared plus 1. So x squared is always positive unless x is 0. So this is only defined for x different from 0. And where is this function increasing and decreasing? We need to look at the derivative. F prime of x, by the product rule, is the derivative of x squared, which is 2x, times the log of x squared, plus x squared times the derivative of the log of x squared. That's 1 over x squared times the derivative of x squared, which is 2x. So we get 2x, the log of x squared. I'll just leave it like that for a moment. And here I have plus 2x. When is that equal to 0? So this is equal to let's see. So let's actually look at this more carefully. Remember that for x greater than 0, the log of x squared is 2 log x. So let's first look at the case when x is greater than 0. So for x greater than 0, f prime of x is 2x times 2 log x plus 2x is 4x log x plus 2x. When does that equal 0? That's equal to 2x times 2 log x plus 1. And if this is equal to 0, 2x is positive. So 2 log x plus 1 equals 0. So log x equals minus a half. So x is e to the minus a half, or 1 over the square root of e. Right? For x positive, this is where the derivative is 0. And but let me say more than that. When is the derivative positive and when is the derivative negative? So I have f prime of x is 2x times 2 log x plus 1. This is greater than 0. This is always positive. So this is greater than 0 if and only if x is greater than 0 and 2 log x plus 1 is greater than 0, which means log x is bigger than minus a half, which means x is greater than 1 over the square root of e. And f prime of x is less than 0 for 2 log x plus 1 less than 0, 2 log x less than minus 1, or log x less than minus a half, x less than e to the minus a half, or 1 over the square root of e. So on the positive x-axis, here's 1 over the square root of e. When x is bigger than this, the function is increasing. And when x is less, the function is decreasing. And what about for x negative? For x less than 0, f prime of x, again, this is 2x, 2 log, well, for x less than 0, log of x squared, this is, let me go back and do this more carefully because this requires a certain amount of analysis. So again, this was number 29. We have the function f of x equals x squared log of x squared plus 1, which is the same as x squared, the log of the absolute value of x squared plus 1. And if x is negative, then absolute value of x is certainly positive. And we calculated f prime of x. Let me do it again. F prime of x is 2x times the log of the absolute value of x squared plus x squared times the log of the absolute value of x, which is, so this is the same as 2x squared log of the absolute value of x plus 1. So f prime of x is 4x log of the absolute value of x plus 2x squared. The log of the absolute value of x is 1 over, the log is 1 over the absolute value of x times minus 1, which is 4x log x plus 2x over x. F prime of x is 4x log of the absolute value of x. Let's see, that's what I had the last time. Plus 2x. Let me just sort of explain something. So if you have the function f of x equals the log of x, this is only defined for x positive. And the graph looks like that. If you take the function f of x equals the log of the absolute value of x, this is equal to the log of x for x positive, the log of minus x for x negative. And the graph of that function for x positive is the usual logarithmic function. When x is negative, it's the symmetric function. It looks like that. Here, the derivative is always positive. Here's the derivative is always negative. If f prime of x is if f of x is the log, the absolute value of x, and x is negative, f prime of x is equal to, well, we can do this in two ways. It's the log of minus x, the derivative of the log of minus x, which is 1 over minus x times the derivative of minus x, which is minus 1, which is 1 over x again, which is negative. So in our problem, when we differentiate, we get f prime of x is 4x log of the absolute value of x plus 2x. When we set that equal to 0, we get a symmetric result with 1 over the square root of e as being the point where the derivative is 0. I don't want to spend too much time on this, but the analysis is very similar to and the graphing is very similar to the positive part of the problem. So here is a series of fundamental problems that you will definitely be tested on in the next exam and also on the final. So these are the problems starting with 77. So let's look at number 77. F of x is x cubed minus 3x squared. We want to find the critical points of the functions and use the second derivative test, if possible, to see if they correspond to local minima, local minimum, local maxima. So how do we find the critical points? Critical point is where f prime of x is 0. So for this function, f prime of x is 3x squared minus 6x, which is 3x times x minus 2, and that's 0 at x equals 0 and x equal 2. So these are the critical points. What's the second derivative? Second derivative is 6x minus 6, or 6 times x minus 1. F double prime at 0 is minus 6. So at 0, you have a critical point. The second derivative is negative. So x equals 0 is a local maximum by the second derivative test. What about at x equal to 1? Sorry. What about at x equal 2? The second derivative at 2 is 6 times x minus 2, 6 times 2 minus 1. 6, that's positive. So x equal 2 is the local minimum. And if you were to graph this function, you would have a local maximum at 0 and a local minimum at 2. Oops. Looks like this. Show it better. So here you have your local max at 0, and here you have your local min at 2. And we got that using the second derivative test. Any questions about this? Look at number 80. F of x is x cubed minus 3/2 x squared minus 36x. So how do we find the critical points? We set the derivative equal to 0. F prime of x is 3x squared minus 3x minus 36. See, that's 3 times x squared minus x minus 12. And this I think I can factor into x minus 4 times x plus 3. So this equals 0 at x equal 4 and negative 3. So those are the critical points. If this is the first derivative, the second derivative is 6x minus 3. So the second derivative evaluated at 4, 6 times 4 minus 3 is 21 is greater than 0. So x equal 4 is a local min. F double prime at minus 3 is 6 times minus 3 is minus 21. That's negative. So x equal 3 is a local maximum. Okay. Let's look at some problems where you try to find the intervals where a function is concave up or down. In the same set of problems, number 63, we have the function f of x equals x to the 4th minus 2x cubed plus 1. So f prime of x is 4x cubed minus 6x squared. And the second derivative is 12x squared minus 12x, which is 12x times x minus 1. So this is 0. That's 0 and 1. If x is bigger than 1 here, if double prime of x is positive, and the curve is concave up. If x is less than 0, if double prime is still greater than 0, and the curve is concave up. If x is between 0 and 1, this is positive, but this is negative. F double prime of x is negative, and the curve is concave down. So this curve it's concave up. Let's see, for x less than 0, it's concave up. At x equals 0, it becomes concave down. And at x bigger than 1, it's concave up again. So at this point, x equals 0 is an inflection point. An inflection point is a point where a curve changes from being concave up to concave down, or from concave down, actually this would be the inflection point, from concave down to concave up. So x equals 0 and x equal 1 are both inflection points. Concave up to concave down to concave up. Let's look at another one, maybe more interesting. Suppose this is number 66. Suppose I have the function f of x equals 1 over 1 plus x squared. The first derivative, so this is like 1 plus x squared to the minus 1. So by the chain rule, the first derivative is minus 1 plus x squared to the minus 2 times 2x. Or it looks like minus 2x over 1 plus x squared squared. And the second derivative is when you differentiate this, the derivative of 1 plus x squared to the minus 2 is minus 2 times minus 1 makes this 2. 1 plus x squared to the minus 3 times 2x times another 2x makes that 2x squared. Minus 1 plus x squared to the minus 2 times the derivative of 2x, which is 2. So let's see if I can figure out what this is. This is 2x squared is 4x squared. This is 8x squared over 1 plus x squared cubed minus 2 over 1 plus x squared squared. If I want to put this over a common denominator of 1 plus x squared cubed, I have 8x squared minus 2 times 1 plus x squared. This is 8x squared minus 2x squared, 6x squared minus 2 over 1 plus x squared cubed. So this is the second derivative. I can write this as 6 times x squared minus a third over 1 plus x squared cubed. So the sign of this is always positive. Sign of this is completely determined by this. So f double prime of x is greater than 0 for x squared greater than the third, or x, absolute value of x, greater than 1 over the square root of 3. And f double prime of x is negative for the absolute value of x less than 1 over the square root of 3. So here, the curve is concave up. Here, the curve is concave down. So if I have 1 over root 3 minus 1 over root 3, here, the curve is concave up. Here is concave up. Here is concave down. So these 2 points must be inflection points. Yep. And all of this information can be used to graph functions. So let's look at this one problem, or maybe 2 more problems where we are graphing. So now I'm moving to the next section. It's all the same subject, page 278. Suppose I want to graph using all the information that we now have, the following function. Let's look at number 19. And I'm going to look at the function. It's a quartic curve, x to the 4th minus 6x squared. So I want to use all of the calculus, derivative calculus we learned so far on this function. We want to find the local max and minima, where it's increasing, where it's decreasing, where it's concave up, where it's concave down, where it has inflection points. So we take the first derivative, 4x cubed minus 12x. which is 4x times x squared minus 3. So f prime of x equals 0, at x equals 0, and plus or minus the square root of 3. So these are the critical points. There are 3 critical points. What's the second derivative? It's equal to 12x squared minus 12, or 12 times x squared minus 1. So the second derivative at 0 is minus 12. So x equals 0 by the second derivative test is a local max. What's the second derivative at plus or minus root 3 is equal to 12 times 3 minus 1, or 24. So we have 2 local minima, plus or minus 1 over plus or minus square root of 3. These are local minima. And what's the value of the function at these points? This is f of x. So f of 0, of course, is 0. F of plus or minus root 3 is going to be plus or minus root 3 to the 4th minus 6 times plus or minus root 3 squared. So root 3 squared is 3. 3 squared is 9. Minus 6 times 9. Root 3 squared is 3. Sorry, root 3 squared is 3. So 6 times 3. And this is root 3 squared squared. 3 squared is 9. So this is equal to minus 9. So if we want to graph this function, f of 0 is 0. Let's make this 3, 6, 9. So f of 0 is 0, and f of 1 over f of root 3, which is about there, is 9. And f of minus root 3 is about 9. Oops. So this is minus root 3, and this is plus root 3. So here we have local maxima, and here we have local minima. What about the second derivative? We have f double prime of x is 12 times x squared minus 1. This is greater than 0 if the absolute value of x is greater than 1, and less than 0 if the absolute value of x is less than 1. So from minus 1 to 1, the curve is concave down. Bigger than that, the curve is concave up. So we have inflection points at x equal plus or minus 1. The value of the function at 1 is 1 minus 6, or minus 5. It's about here. And plus or minus 1, it's minus 5. So from minus 1 to 1, the curve is concave down. And let's see, we have a maximum. Sorry, that's true, but I don't really need these points. Maybe I do. F of 0 is 0. F of root 3 is minus 9. Minus 9. Should have done this properly. Minus 9, down around here. Okay. So here we have a local minimum. The curve is concave up. Here we have an inflection point, concave down. Here we have an inflection point, and it's concave up again. So this is what our study of calculus gives us. the curve, the graph of this fourth degree polynomial has a minimum, a max, and a min. That's the general shape of a fourth degree polynomial. And here are the two inflection points, concave up, concave down, concave up again. That's the story. And I encourage you to spend as much time as possible on Pearson's MyLab, working problems using these applications of the derivative, and also do some problems from the book that you solved longhand. They're very useful. Okay. Any questions before we quit for the morning? I will have a few office hours that I post during the spring break, just in case you have some questions and you want to ask me. I'm very happy to be available. Or if you have questions and you can't make one of the posted sessions, then just send me an email. We can arrange a time. But we're now about to be, for this class at least, on break. And our next class is 2 weeks from today. Any questions before we leave? Okay. Thank you all. See you in 2 weeks.